All right, so it's good to see everybody back again for a second day. And join me in welcoming Man-Chun Lee to talk about stability problem in scalar curvature using Ritchie flow.
Okay, thank you so much for the invitation. So I hope it's informal. So I don't want to put it too serious. Okay, so I'm going to talk about. I just want to share with you guys some of my thoughts using geometric flow towards completeness problem in scalar curvature. Some of them is not very satisfactory, but I still want to share my thoughts with all of you. So let me start with the motivation. I use it all the time. Major motivation is to consider a sequence of Riemann manifold with a certain kind of curvature constraint, and then we want to ask the general question like, first of all, can we extract convergence of sequence? Secondly, what do you mean by convergence of sequence? In what kind of sense you can talk about the convergence? And more importantly, can you identify the limit in whatever sense you try to? Okay. And then, of course, if you have some weak convergence, so of course, you can't expect too much. So, but under what kind of weak convergence you can talk about something about the limit. Okay, this is the main philosophy behind all this. At least to myself, I want to study this kind of question, and then, of course, if you strengthen the curvature a little, a lot, like if you talk about the sectional curvature, then all the theory are understood using the Alexander space theory. So by understood, I mean you can talk about the convergence, you can talk about what topology you are taking the limit, you can make sense of the limit, which is a metric space. You can also make sense of the curvature lower bound on the limiting manifolds, limiting metric space. So everything is well understood using the Alexander space theory on the sectional curvature. And then for Ritchie curvature, we can we still have the good theories based on the optimal transport and the Giga coding theory. Of course, by now we know the RCD theory, which basically say that the Ritchie lower bound is equivalent to say that the Botner formula works in some W12 sense. Okay. On metric measure space. Okay, so yeah, so of course, just a quick overview. So we can talk about the convergence of sequence in terms of the Gromov-Hausdorff topology measure, or more precisely, the measure Gromov-Hausdorff topology if you assume the volume non-collapse or even collapse. Yeah, this is basically what I just said. And then, of course, very importantly, the Ritchie curvature case, you have to pay with the measure. Okay, this is a key improvement from the Alexander space. And then, for sectional curvature, we can talk about sectional curvature lower bound for the limit. And then for Ritchie lower bound, we can still talk about the Ritchie lower bound by making use of the Botner formula. If you talk about the RCD, or you can talk about some entropy monotonicity if you go back to the first approach by Lord, Vidali, and Stam. Okay, but anyway, we are mostly concerned with the scalar curvature, so you need to know what to expect first of all. And I know Somani has given a lot of examples yesterday, but let me still recap, or let me still tell you what I try to think of in the first place. So first of all, I try to think about the question in terms of the rigidity first, because this is essentially the baby question of all this problem. And then, of course, in Ritchie geometry, we know we have volume comparison, so which basically say that the Ritchie lower bound together with the volume upper bound, volume lower bound will force manifold to be flat. Okay, and then if you want to ask the same things for scalar curvature, then you ask something like, oh, scalar here, and something, I don't know, something, and which force curvature to be zero. Okay, so here comes to the most important theorem in scalar curvature geometry by Shen and Yao and Gomov-Lawson, which says that the torus has a vanishing Yamabe types, or equivalently the scalar curvature here plus torus imply flat. Okay, so this is replaced by torus. So there are some topological constraints. Okay, and then of course we now know the topological constraint is quite crucial, and one of the basic questions which restricted to this case is okay. So now because we have rigidity for torus, so I just restrict ourselves to torus. Okay, this is actually in parallel with the positive mass theorem, which is our main theme of this workshop. Okay, you will see that if we have some idea to handle this problem using geometric flow, then we will be able to answer the same question for the positive mass theorem. So I mean, in the way I formulate the question, then they are basically equivalent. Okay, at least to me. Okay, so the question by Gomov is asking if the scalar curvature has a almost non-negative scalar lower bound, then he tried to find the correct topology which the sequence will sensitive to the torus, to the flat metric. Okay, like what we expect, because the limit must be in some sense a non-negative scalar curvature, so it must be in some sense a torus. Okay, but what is the some sense you are looking for is the question. Okay, and then of course you can't expect too much if you don't have anything else, because the manifold can be expanding, can be collapsing. You need some non-collapsing and non-expanding assumption to make sense of the whole question. Otherwise, the manifold will just expand to the Euclidean space of collapse to a point, which makes no sense to talk about all this question. Okay. So in rigid geometry, we have volume comparison, but this is very restrictive because we have volume comparison. So volume long collapse globally is equivalent to say that volume is long collapse locally. So yeah, this is reasonable for rigid geometry, but it's not clear what to impose for scalar curvature. Okay, and then like I say, we are trying to look for the weak topology here, but I want to point out that Kolmogorov topology is in general not possible. Okay. So I'm stealing some picture from a paper of Somani. So you should ask. Okay.
Hey, wait. Somani Wenger.
Oh, sorry.
Sorry.
Yeah, you're right.
Also Stefan Wenger, just to be fair. Yes, thank you.
Okay.
Wenger. Okay. Yes.
Yeah, but maybe I steal it from your survey. That's why I put it on my paper.
You may steal it from my survey, but I stole it from that paper.
Okay. It's hard to trace the real source. Anyway, so this picture basically says that you can't expect the Kolmogorov topology because I mean, if you take a look on this one, you expect something like the sphere happen at infinity. But if you take the Kolmogorov topology, you get something weird here, okay, which is not the supposedly correct limit. Okay, so okay, but this picture is weird in the sense that the limit is really singular. So if you assume the limit is quite regular, then things become different. Okay, I mean, if you insist to focus on something very regular on the limits, then you will see this one. Okay. I mean, you should see this one. So this is my question. Okay, so what do I say? All right, so this is the next testing case, which is easier than or the question I raised at the very beginning. So if I assume we have a limit which is smooth, but the convergence is a weak convergence, okay? Yeah, okay, of course, this is still a question, but assume we have regularity on the limit for some reason, then if I'm focusing on the case when the sequence have a lower bound like this, okay? Then if the weak convergence is like the continuous topology, then do we still have a scalar curvature non-negative? Okay, and you can also ask the same things, which is motivated by the positive mass theorem with corner, which says that okay, if you have a smooth limit, which the convergence is smooth away from some singularity, okay, then can you identify the metric geometry of this smooth limit? You only know the regularity, but not the real structure. Then can you identify the limit? Okay. That means we only pass the scalar curvature away from we can only pass the scalar curvature lower bound away from singularity. Okay. Pass the scalar curvature lower bound information to limit away from some singularity. Then can you still talk about the limit? And of course, you should also ask if the weak convergence is Goldman-Hausdorff or uniform distant convergence or intrinsic flat convergence. Then what do you expect? Okay. Okay. So but it's very easy to see that if you only focus on Goldman-Hausdorff topology, then you can't expect too much because you can build a tunnel by Zhang-Yao, Gomov-Lawson's construction. You can just keep building the tunnel so that the topology is really complicated, but the scalar curvature is still positive. Okay, so I will at first ignore the Gomov-Hausdorff topology in this types of question. Okay, but you can still ask something else. Okay, but let me. Okay, before I talk about some of my thoughts, let me mention some earlier works. So now at this moment, I don't insist considering the torus. I just focus on some random manifolds. Okay, but assume this two condition, scalar almost non-negative, or you can actually replace it by something else. Then the question is fully answered by Gomov and Balmer. And if you take a look on their paper, so their approaches are very different. So in the paper of Gomov, he basically find an alternative definition of scalar curvature lower bound only based on the inner product structure. So you need to talk about the angle, you need to talk about the length. So as long as you can talk about both stuff, then you can talk about the scalar curvature lower bound. Okay. And then, so I like the approach by Balmer, which is based on Ritchie flow, which I'm going to talk about it more. Okay. Anyway, their method also proved that, also confirm what we expect. We have a semi-continuity on the scalar curvature. Okay, and I just want to point out Gim has generalized it a little bit further, which only require the limit to be a continuous metric. Okay. Okay. So anyway, because of all this, if M is torus, then you can say that the limit must be automatically torus. So you can think of this as a bootstrapping. So if you know the limit is smooth, then you automatically improve it to be torus, okay, to be flat torus. Okay. You can think in this way. Okay. If you have some regularity at the very beginning, you can improve it to be flat torus. Okay. Okay. So what do I want to say here? Yeah. So there are some alternative questions like if sorry, what I want to say. Okay, if we relax the convergence to some other weak sense, some weaker sense, then can we still have the same things? Okay, this is the question I am mostly interested. And then what do I want to say? Oh, sorry, I don't want to mean, I don't mean to say something like this. Okay, I want to point out the next example. So because we are looking for some relaxation of a Gromov result. So basically, I'm trying to find a better, find a weaker notion of this convergence. So as I have said, the Gromov-Hausdorff convergence can't be the correct one because you allow the topology to be changing, which complexify your whole sequence. Okay, and in my baby question, they are not allowed because I just fixed the manifold to be a torus. Okay, so then Peter Topping and I try to answer this question, and then we are able to give a negative answer when the dimension is bigger than or equal to 4. So we basically say that if you fix a if you fix a torus of sphere, okay, we just need to fix some space form to make some argument works. Okay, like the torus. Okay, say for example the torus. So you just simply fix some random function. Okay, that means you fix a conformal metric, which is conformal to the flat torus. Then you can always find a sequence of Riemannian metrics on torus, which is uniformly L infinity. Okay, uniformly by ellipsis, uniformly GI. Oh, sorry, GI is uniformly L infinity. Okay, which and then still satisfy the scalar curvature law band, such that the distance is convergent to this conformal metric. So of course you can choose some random function f such that this metric is not positive, it's not of non-negative scalar curvature. Okay, the scalar curvature of this one can be crazy, right? Because I only require f to be continuous. Yeah. This is just a random metric which is conformal to the factors. So the scalar curvature can be anything. I'm not anything, but at least not non-negative. Okay, so it basically says that even if you strengthen the distance in dimension bigger than or equal to 4, you can't expect too much. Okay, and actually, in fact, the sequence has almost. This is very rough. So this has a almost non-negative loss of constant along the sequence. So in some sense, the sequence is like the factors if you read it in terms of measure. Okay. This is based on, so this example is constructed based on my example with Warburg and Aaron. Okay. With some modification. And then more importantly, okay, if you are more interested in intrinsic flat convergence, then this assumption will imply the limit, the convergence is also in the intrinsic flat sense. Okay, so that means if you forget about the measure, only focus on the metric structure, like the distance or intrinsic flat convergence, then you can't expect the scalar curvature will be preserved locally. Globally, maybe yes, but locally, definitely not. Okay, so you can't draw the same analog of a Gromov film. Okay, but I want to point out. So let me have a quick overview of the construction, and then you will see what kind of convergence you should impose in order to make the film works. So the construction of our work is based on this building block. Okay, so basically I view the torus in terms of doubly well-ordered coordinate. Okay, so these two coordinates correspond to the R3, and the last one corresponds to the last R1. Okay, and then roughly speaking, the torus, the standard torus is when alpha is identical to 1 and beta is identical to 0. So this one is 1, this one is also 1. So this is standard torus. Then standard Euclidean space modulus the quotient. Okay, but we do it in a way that we put alpha sufficiently slightly smaller than 1 so that it becomes a cone on. So on the first 3 coordinate is like this is like a cone here, okay, with some certain cone angle, okay. So but as long as the cone angle is not pi, then you will generate infinite positive scalar curvature nearby the tips, okay, because the scalar curvature is like 1 over r squared. So I mean epsilon over r squared. The epsilon depends on the cone angle. So generally a lot of scalar curvature which dominate the degeneracy from beta. So because of this is basically infinite, so you have some room to change the beta, okay, so that the beta can even be negative infinity, okay. But this is basically the building block of the whole construction, and then we iterate the building block along a lot of direction, okay, but we just do it in a very tiny region, okay. Every time we apply the building block in a very tiny in a very tiny region, ds here, okay. So by iterate this building block on the torus along a lot of direction, then you will see that the metric will, okay, because the destinated metric is a conformal metric which is strictly positive. So we adjust it in a way that is always uniformly by ellipsis, okay, because I can always adjust the degeneracy, which is not too much, because I'm looking for something strictly positive. So I adjust the degeneracy depending on the destinated metric, okay. And then the way I construct with a cone angle will guarantee that the scalar curvature is almost non-negative, okay, because yeah, of course with some cutoff argument. So you can recover the standard metric from the cone, okay, slowly, okay. It makes the scalar curvature only almost non-negative, okay. And then we adjust the beta, adjust the degeneracy carefully so that it's close to your ultimate metric, okay. But because in this way, because every time we do the modification only within a really tiny region, so no matter how you do it, because you do it with a really very small scale, so the sequence will still close to the flat metric in an LP sense, okay. This is very important, okay. It's basically a guide to me saying that, okay, of course, if you look at the distance, this is not correct, because this is not correct. This is the third item which basically says that the distance is not correct measurement sensitive to the scalar curvature, okay. In order to sensitive to the scalar curvature, you have to look at the LP geometry or measure theoretic geometry, okay. Something like this, okay. You need to look for you need to focus on some convergence related to the measure, just like the rigid geometry. You need measure metric space, okay. Without the measure, you can't talk about the rigid curvature. But likewise, you need something similar, okay.
Wait, can I ask a question about that?
Yep.
Can you just elaborate on this LP sense? Because there should be some kind of fixed gauge in which you talk about the LP norm.
No, in this case, you can fix the ambient metric. Like the GI is a sequence of tensor minus the flat with respect to any metric you like, and LP converges to 0. This is what I mean. Yeah. It's only the classical one, right? Because I fixed the gauge I fixed the coordinate basically. I don't care intrinsic geometry anymore. Just fix the ambient space. Yeah.
So, but I'm just wondering, do you consider that a choice, or is that, do you think of that as like a canonical choice, or
LP, I don't know, this is
or I mean, okay, so you're choosing to compare them in the, with respect to the flat metric and the same coordinates somehow, like there's a constant diffeomorphism or something. I'm wondering
Yeah.
if you think of that as a choice, or if that's comes with the problem somehow, or
I mean, the flat metric isn't even close to itself in LP, right?
Yeah, I know what I mean. I know what I mean. But yeah, this is another question. But because I only think of the question in the baby question. I'm only thinking the baby question, like this sequence of GI convert to some
Sure.
smooth metric, but in the LP sense, along some fixed coordinate, in some fixed coordinate.
Yeah.
I only think about the question in this way first, like the Gomov film. Okay, so
right. Oh, yeah, and then can you also say, you said you made some comparison to a measure for Ricci curvature convergence. What do you what do you suggest as an analog of measure, or
I don't know.
okay?
because this is the question remains unsolved, so that's why I don't know
Sure.
how to move forward.
Okay, so something related to this. I see. Okay.
Yeah, in fact, if you take a look on Gomov lecture, he think this is true. I mean, the setup I raise here, he think this is the he's like saying that this is expected to be true. We even without this assumption, even without the uniform biellipsis assumption. Oh, but he is talking about measure. Sorry, measure. Okay. Yeah, but of course, once you answer this one, you have to move on and talk about the question you guys raised. But I don't know how to fix this one, so I don't want to bother too much.
Yeah, thank you. Thank you. Yeah.
Yeah.
Can I just ask a question? Your point,
Yeah.
when you say DGI is close to any conformal metric, what's the closest?
I mean the D
Uniform?
I mean this by close I mean this statement.
Yeah, it's uniform convergence. Okay.
Yeah, this uniform convergence. Yeah, the conformal. I don't think the conformal is very important. It just makes our argument easier.
Just for your argument, yeah.
Yeah, but I only want to get a negative answer. So
Exactly. No, this is interesting. Okay, thanks.
yeah. Okay, so anyway, this suggests me that this question should be correct. I mean, this is the setup which should lead some correct answer. So it's affirmative answer. Okay, this because of this construction. Okay. Yeah, this is basically what I just said. Yeah, so it weighs if you have sequence of metrics on torus, which is uniformly by ellipsis and almost on negative scalar curvature, then the sequence should converge to some flat metric in some integral sense. Okay, based on the example construct here. Okay, and then of course I do it very roughly because I don't know what is the correct integral sense. So I did some try. So let me share with you guys. So okay, at some point I believe the answer must be reflected by the geometric regularization. Okay, at some point I believe this is correct, but now I'm not sure because of what Anton did. So I'm not sure now. Maybe just because I can't do it maybe just because I can't get the correct estimate on the Ricci flow. But anyway, so at some point I believe this is I believe that if the convergence is correct, then it must be reflected by some geometric regularization. Okay, so I try a lot of things like Ricci flow, Yamabe flow, Man-Chun flow, etc. And then so the baby idea is okay. I'm okay. Let me tell you, I'm quite obsessed with the biellipsis assumption. Okay, because of some reason, because I'm from complex geometric. I learned math from. I mean, I'm from complex geometry, so the biellipsis data are quite like what are quite in complex geometry, that if a data is bi-ellipses, then it's very easy to get regularity, okay, because of some Carby-Yau estimate. So that's why I like this types of assumption. And then it's also natural because of the example I get, and it also implies any long collapsing you like, usually like Scalar, Poincare, volume, etc. So that's why I like thinking the question based on this assumption. Okay, so then the problem reduces back to getting some regularity from this bi-ellipses data, okay, for positive time. And of course, you need to preserve the scalar curvature law along any flow you like, any geometric regularization you like. I mean, otherwise you are not using the correct smoothing. And then once you get the regularity, you can get compactness. And then the problem is reduced back to ask what kind of time series regularity of the geometric flow you have in the weak stance. So if you have bounded curvature, then the time series regularity is very easy, just C1 alpha. Okay, if you have, I mean usually, okay. But if you have no regularity at all or very weak regularity, then sometimes you still get some time series regularity, okay. But you need to identify them, okay. Yes, but by time series regularity, I mean to get a uniform convergence, okay, weakly, but uniform in I. Okay, so that means the convergence is weak but still uniform in I, depending on the bi-ellipses assumption that you set up at the very beginning. Okay. So then I just changed the question from a geometry question to a PD question, basically to find the correct stability notion that you can raise in based on the bi-ellipses data. Okay, this is what I try to interpret the question. Okay, so I try some obvious choice like the Ricci flow, Yamabe flow, or Man-Chun pair flow, and then I guess something. Okay, but the reason why I think this is this is correct, because if we compare with the Chiga coding theory, the Chiga coding theory is the stability of the stability statement in the Chiga coding theory basically says that okay, the volume comparison is rigid, and then if the volume comparison is almost like Euclidean, then you get the Gromov-Hausdorff closeness to the Euclidean space, right? This is the famous theorem of Chiga coding. And then although the Ricci flow is not I mean, it's not immediately clear why the Ricci flow is useful there, but there is a Ricci flow proof on that stability statement. And then the Gromov-Hausdorff topology is exactly appearing when you are careful enough on the Ricci flow argument. The Gromov-Hausdorff convergence actually appear from the analysis. So that's why I say, okay, now of course we don't have Ricci curvature. Okay, we only have scalar curvature. Then if we mimic the Ricci flow proof of the Chiga coding theory, then we should get something. Okay, this is what I believe in the past. Okay. Okay. And then let me tell you what I have tried. Okay, this is based on a joint work with Man-Chun. We try using the Yamabe flow and then mix is and then we prove something like this, which is motivated by result of Alan Bryan. Okay, which says that okay, suppose I'm in this case HI can be a sequence of metrics. I mean, basically saying this HI is representing a sequence of conformal class, which is in some sense compact. Okay, I assume the uniform boundedness of the conformal class. And then, okay, so if you fix the well-behaved good behavior of the conformal class, and then I just look at the candidate that I'm interested in, the GI is a uniformly biliptious within the sequence of conformal class. Okay, then together with all the previous assumption like scalar curvature lower bound and the sequence of HI can't expand and can't degenerate with bounded Ritchie geometry more precisely. Then with this well-controlled reference, the GI will converge to the flat torus in this case. Okay, in the metric homomorphic topology and also in the LP sense modulus the diffeomorphism. And yeah, I just want to point out you can relax it a little bit more. Okay, so basically the theorem is okay, of course the homomorphic convergence I'm not sure if it's surprising because we fixed in some sense we fixed the conformal class, so you can pretend HI is the flat torus, okay, which is the standard case, okay, but we can also allow the HI to be changing, okay, and then the main implication here from this theorem is that if the distance go crazy, then the conformal class must also go crazy. Okay, this is well, I mean, okay, this is the theorem, what the theorem says. Okay, if the distance is not converging to the correct one, then the conformal class also can converge. The conformal class also cannot be well controlled. Okay, when you compare with the example I did with theta topic, then this is essentially what we say. Okay, and then this
Can I
is
ask quick question? What is under the previous setting? What are the other assumptions here?
I mean the scalar curvature here. I mean the, sorry, I should just raise here. Scalar curvature of GI is bounded from below by one. Okay, I should be more clear here. I just want to give you a rough idea what does it mean. HI with uniform bounded geometry, that means okay, there are some versions, but like this one in strategic radius. Oh no. The volume of HI is bounded from below, and this diameter of HI is bounded from above, and together with this one. Okay.
All right, thanks.
Yeah. Okay. So this is what I try using the.
I'm sorry, do you need a subsequence for this?
Yeah. Sorry, it's subsequent.
Okay.
Yeah.
And the other question is, and is there a dimension restriction on this?
No.
All dimension.
Yeah, all
Okay.
dimension. But it's very restrictive because I fixed the conformal class. So the question reduced back to study the function only. I mean, of course, the gauge is also changing, but the way it changed is well controlled.
Yeah.
So it's not
Right.
It's not really flexible. It's still fixing. Yeah. Okay, and then I tried something else. I tried the Scalar case. Yeah, it's totally irrelevant to scalar curvature, but it just tell me what else you can see from the geometric flow. So by Scalar, I mean the following. So I'm considering the Scalar case, which is okay, the torus is now a complex torus. Okay, a complex torus. And then GI is a sequence of Scalar metric. Okay, but I don't restrict the Scalar class. I just restrict it to be Scalar. Okay, no Scalar class. The Scalar class is changing. Okay. Unlike the conformal case, the conformal class is fixed. I mean well controlled, but now the Scalar class is not well controlled. But because we are in the bi-ellipsis well, so the Scalar class, although not a priori controlled, but this assumption is basically restricting your Scalar class in some sense. Then the GI will converge to the standard flat torus. Standard Scalar flat Scalar torus. Okay, in terms of in the sense of current. Okay, this is a study. The sense of currents. The convergence in terms of current is well understood in complex geometry. They use it all the time. So I'm just saying that, okay, in this case, we can get the same things using the same philosophy, okay, but playing around different analysis. And then I think it's quite interesting that in this case, the flat metric, the metric will always drop below the limit. Okay. Okay. It's like the opposite of the distance below volume above. I don't know why it's appear here, but if you can prove the opposite, then it's much better. I think you can prove some. Yeah, this is anyway. This is the distance below, distance above, volume the same. Yeah, but you can't use it to tell too much about the intrinsic flat convergence because it's not a good barrier. And anyway, this is the things I can prove using the Man-Chun pair flow, but in the Scalar setting. In fact, you can also do it in the Hermitian setting, but I did try using the compressify the real torus to a Scalar torus and compressify the Riemannian metric to a Hermitian metric, but it doesn't work. Okay, the scalar curvature will becomes terribly uncontrolled. So yeah, I just tell you what we have tried. Okay, I tried using some Scalar geometry before. If you assume something Hermitian, not even Scalar, if you assume something Hermitian, then you are very close to the answer. Okay. In fact, you can even prove you can even give an alternative proof to the torus rigidity if you assume Hermitian. Much easier, just 2 nice or 3 nice. Yeah, but I don't know how to turn Riemannian torus to a compressified torus without changing too much the scalar curvature. Okay. Yeah. Anyway, this is another story. Okay. But anyway, all this theorem basically tell us the integral convergence seems to be a reasonable measurement, at least in this in view of the example I did with Peter Topping and in view of all this complex sphere with Man-Chun, seems to be a sensitive notion to scalar curvature in some sense. Okay. Yeah. And I believe some of you already know this. I just want to point out. So another related works which is related to the DP convergence. Yeah, but maybe not. It's very. Yeah, we can also talk about the DP convergence, but I believe most of you already know this, so I will skip it. But sorry.
Remember, you end in 15 minutes.
Okay.
At 1:15, not at 1.
Okay. I still have 5 slides though.
Yeah. Okay. You have 15 whole minutes. Yeah.
Okay. Hopefully too much for me.
Well, you're skipping slides, so I was like, if you're rushing because you think you're out of time. Yeah.
Oh, sorry.
No, it's okay.
All right. So okay, finally I go back to the Richard flow, go back to the title. So essentially the question is to ask okay, I reduce back to a Richard flow question. No, forget about the scalar curvature, just some random Richard flow question. So then the question is under what condition you can deform the metric using the Richard flow? Okay, using the Richard flow. Under what kind of subsumption you can deform the Richard flow with uniform estimate? Okay, uniform estimate. So of course, you may ask why Richard flow or why Yamabe flow and why Man-Chun pair flow? Because okay, this is bias. I'm from Richard flow background. That's why I say I mean it's most canonical. Okay, and then the Richard flow will preserve the scalar curvature law band. This is the key point of the whole of all this stuff. And then yeah, and to be honest, to be honest, if you in the question I raised, if you fix the manifolds, fix the underlying coordinate, and then ask the stability question like Gomorph, then you should not use the rigid flow, because rigid flow is a diffeomorphic invariant. So if you use it, you lost the coordinate. You will turn everything into an intrinsic question. So usually, at least when I deal with all this question, I will not focus on the rigid flow, but I will focus on the so-called the rigid detect flow, which I don't know how to give you a really quick idea, but roughly speaking, this is the rigid detect flow is rigid flow modulus the diffeomorphism. Okay, so locally, it looks like this. Okay, it's like the I still have some term. I think it's G, something like this. Okay, something like this. So this is the rigid detect flow, okay, which is diffeomorphic to the rigid flow. And the main reason why this is more user-friendly, because this is strictly parabolic. Okay, and then and then also, you can also see that this is not linear, and then the non-linearity is pretty much like the harmonic mapping flow. So you have a quadratic term here. Okay, you have a quadratic term here. So that means as long as you can control the C1, you can control the rest. Okay, just like the harmonic mapping flow, as long as you can control the energy density, you can control the rest. Okay, so for rigid detect flow, which is for the rigid detect flow, as long as you can control the C1, you can control the C infinity. Okay, this is just a linear term, so you don't have to deal with it. You can. This is always well controlled. Okay. Okay, so all right. So because of the question, I focused a lot on the L infinity. Okay, so I basically saying that okay, without the special structure, but with L infinity assumption, okay, then can we deform the rigid flow? So the theorem I proved with a Genshin tool. This is a simplified version. It's also working for long compact manifold. In fact, most of the theorem I mentioned today is routine enough to deal with the long compact case. Okay. Some of them even without. You can also deform it without bounded curvature. Okay. Some of them, like this one actually. Okay, but I only focus on the torus. So yeah. But yeah. Okay, so we are proving the following. So suppose M is a closed manifold, okay, and G is a W1N metric intercept with L infinity. So W1N intercept L infinity is like, it's very similar to the continuous metric. Okay, if you are in W1P, P is bigger than N, then you can embed it in the C0. Okay, so when P is equal to N is basically the borderline of the Sobolev embedding. So, and that's why I said this is parallel. Okay, they are not correlated with each other. Okay, so if you assume the singularity like this, okay, then you can flow it by the rigid detect flow. Okay, I should not say the rigid flow is cheating. Yeah. Okay, we can flow the rigid detect flow from this initial data. Okay, from this initial singular data. Okay, which becomes smooth and converge back to the initial data in W1N. Okay. In fact, we also have stability statement on this in this setting. Okay, and yes, the theorem here is based on the concentration argument used in what using the concentration argument, which requires the W1N structure. Okay, Yep. So yes. Okay, and then you can see that. Okay, so now the theorem here basically have everything, all the ingredient we need to talk about the stability, because now you see that this is essentially the time zero regularity. Okay. Okay, this is the regularity for C infinity regularity. And then, yeah, okay. So if you apply this to the sequence of metric, you can get the following. Okay, if you apply this to the sequence of metric that we consider, then you can prove the following. Okay, we haven't used anything about the torus structure, so I just put it in a slightly more general form. So as long as you know the manifold is not PFC, and then you can always find epsilon depending on your reference. Okay, because you need to emphasize. I mean, you have to declare what you mean by W1N. So I declare it. We declare it by fixing a background metric. Okay, so by W1N, that means in a sufficiently small scale, the W1N norm is bounded. But let me phrase it in this way. So you can always find a what should I say, is a threshold for depending on the reference, depending on your background, such that as long as the sequence is close to this reference metric in W1N. So the way I formulate is essentially saying that GI0 is close to H in W1N. Okay. You can also think in this way: it's close to a background metric H in W1N. Okay. Then you can flow it. So once you can flow it, you have uniform estimate, and using the argument that I just said, this is a preserve along the flow. So the argument is like this. So the GI is something I want to study. I regularize it a little bit. GIT. Okay. I know this is uniform W1N here. So the time zero regularity is saying that the flow will link back to the initial data weakly in the W1N sense. Okay, then we have all the regularities, so we can pass it to limit. Okay. So once you pass it to limit, the scalar curvature at the limit is non-negative. Okay. So which says that G infinity T is flat. Okay, if you talk about the torus. And then the time zero regularity is still preserved. So this is still close to each other in W1N. So that's why at the end you can prove that you can find a Richard flat metric, which is the limit of your flow, such that this sequence will close to it. Okay, in the W1N. Okay, by Soberfeld thing, I changed it to LP because this is what I want to prove. I mean, this is a version of the stability that I want to prove. So I emphasize the LP here. Okay. Okay, modulus the diffeomorphism, because when you pass it to limit, maybe you change the diffeomorphism. I mean, maybe you choose you pick some other coordinates. Okay, that's why I need to modulus the diffeomorphism. Okay. And then this is a quantitative version of the stability statement. Okay, based on the existent theorem of Richard flow. Okay. And all right, so let me raise some question. So you can see that all the gas are based on the example in high dimension, but I don't know how to make the example working in 3 dimension. This is related to the conjecture by Somani. And then okay, although the type I should say something about how it linked back to the positive maximum. In fact, in fact, as I have said, so the theorem here, it's also working for non-compact manifold. Okay, as long as you specify what you mean by WNN careful enough. So all the theorem also works for non-compact manifold, even without bounded curvature. So it also applied to the positive mass theorem setting, because for positive mass theorem, if you fix the asymptotically flat end, then you automatically have bounded curvature at infinity. So as long as you have W1N, uniform W1N in the compact region, then you can flow it by rigid flow, and the rigid flow will preserve the AF, the asymptotically flatness condition, and also the positive, and also the ADM mass. So the strategy I outline will give you almost the same things. I mean, give you some counterpart of the positive mass theorem. Okay. The only things we change is the last step we make use of rigidity of positive mass theorem or rigidity of torus, okay, to get some fatness, okay. Then you can get some statement about the positive mass theorem. That's why I said using the strategy, I try positive mass theorem stability is almost like the torus stability. I mean, almost. You need to clarify some asymptotic, some uniform asymptotic fatness at infinity. So once you can do it, the stability statement is quite similar. Okay, and then okay, so you can see that I instead of using L infinity, I am considering L infinity intercept with I'm considering L infinity intercept W1N, and then you can compare with the result by Balmer or Gim, in which they consider the continuous metric. So why this is important? Okay, why continuous or W1N is important? Because if you think about L infinity metric only, so then the L infinity will give you the singularity model of L infinity metric. I mean, the easiest one that you can think is the metric cone, right? It's a metric cone, okay, which arises as a singularity model if you only assume the L infinity structure. So of course, this singularity model will have a scalar curvature positive, okay, because it's like a metric cone. But however, because this is a cone, it's a metric cone, so the curvature will be like 1/r squared. Okay, so if you try to mimic the elliptic with parabolic, then the flow from this metric cone will have curvature like 1/t, c/t. Okay, the c is huge here, the c is huge here, depending on the cone angle. Okay, so then that basically says that, okay, if the c is large, you can't expect too much from the asymptotically point of view, because what do I say? You don't have the stability statement you expect can't be as strong as this. You can't expect some very nice stability statement. This is what I mean. Okay, I don't know how to put it very rigorously, but because the C is very large here, you don't expect some really nice stability statement. Okay. So, but if you insist continuous metric, then the metric cone model will not appear because when you zoom in the metric, it's like Euclidean. Okay, if you assume C0, then let me put it in this way. So if you zoom in the metric like this, you blow up the metric, you go back to the Euclidean space. Okay. First, similarly, if you assume W1N, okay, although you don't have the sort-of embedding anymore, but if you zoom in the metric, you can also get back to the Euclidean space. Okay, that's why the C here will be improved, like C will become like O1. Okay, it will be like 0 here. The rigid flow will behave very nice in the sense that the curvature, the C on T will be like O1/T. Okay, because asymptotically is a flat cone. Okay, because of this because of CCL or W1N structure. That's why you get something. Okay, that's why you get some regularity from rigid flow point of view. Okay, this is the key point why you get some good estimate. And then because it's O1 over T, O1 over T, you also get some stability. I mean, it's easier. Okay, easier. Okay, but the blow up, this is the blow up picture of metric with only L infinity structure. I mean, the good or bad thing is you can't see the topology using this argument. You can't see the torus topology. That's why the PSC, the torus rigidity structure is not play any role here. So so that's why it's not optimal. Okay, because we're trying to find some torus stability. So that's why you should, I mean, the blow-up procedure should sensitive to the torus stability. I mean, the blow-up procedure, I don't know if it makes sense or not. So the estimate you get should be compatible with the torus rigidity. Otherwise, you can't get something optimal. But torus rigidity is like a global information. It's not like a local information. So that's why I said rigid flow seems to be not a good candidate to look at in some sense. Yeah. But if you are willing to assume something stronger, then you can get something strong. Okay. Yeah, that is what I want to say today. Yeah, thank you.
Thank you very much.
Yeah, thanks for a nice discussion of these ideas. Any questions?
Are you able to control distances at all with Ritchie flow?
No. Yeah, this is also a good question. I mean, without any good control, you can't without any good control, you can't control the distance. This is the problem. I mean, if you can, even if you can get this, you can't control distance in both directions. You can only control distance from one direction. Okay. Yeah, it's actually related to the example I did with Aaron and Robin. So the example I construct with Aaron and Robin saying that, okay, you can start in some sense, we are proving something like this. Okay, you can start with something really degenerate, but suddenly jumps back to the Euclidean space. Okay.
Yeah, but that's a 4 dimensions and up.
Yeah, I mean, no, this is not for 4 time. Yes, it's 4 dimension. Yeah. For 3 dimension.
Anything known about distances in 3 dimensions?
Yes or no? In 3 dimension, the rigid flow behave well if you assume some other things, but not good enough to get estimate.
Mm-hmm.
Yeah, unless you do some surgery stuff, but I mean.
And what about minimal surfaces? How do minimal surfaces behave under Ritchie flow?
In 3 dimension, you have some. I think the width is monotone, as far as I remember, but I can't recall anything else. I mean, especially for high dimensions, it's very unclear. Yeah.
So the width is monotone. That's like Koldi-Minkowski, right?
Yeah. Yes. Yeah. Exactly. Yeah, exactly.
But Antoine, didn't you made some example where like you start with this manifold with no minimals, or like so minimal surface appears drastically immediately or something, but
right. So let's see. Let me remember, that was a long time ago. First, a comment about the width thing. I think the monotonicity of that for under square curvature lower bound, that's due to Marcus and Neves, if I'm not, or at least there's one version of the monotonicity which is due to them.
I was just thinking of an old paper of Koldi-Minkowski when
Yeah.
Perelman first came out, but maybe it was only for spherical.
Okay, yeah, that one. Okay.
So minimal surfaces in general, do you know of Ritchie flow results?
Well,
3D.
so, let's see. So it's been used in the proof of the geometrization conjecture. There's an argument by Hamilton, I think, where you're not looking at the width, you're really looking at, say, minimal torus that's minimizing in its homotopy class. And you look at what it does under the Ritchie flow. And so the Coldini quasi paper is a generalization of that idea to index 1 minimal surface.
Right.
Not necessarily minimizing this. Also, I have a paper where, let me see, I proved something along the line of under the Ritchie flow, you can have appearance of stable minimal spheres, even though the scalar curvature is positive. Okay, thanks.
That was the one that surprised me, that like, it's, you know, that you might immediately incur some minimal surface that you didn't know about at time 0. That was the thing that stood out to me. Yeah.
Right. So the example is that you have some kind of a hook. You have to imagine a 3-dimensional hook, and this hook, because the curvature is kind of weirdly spread on this manifold under the Ritchie flow, some parts are going to get bigger, faster, or slower than the other parts, and that's why there are some minimal surfaces that appear stable minimal ones.
Cool.
I had another question mentioned. So maybe you just mentioned this, but so what happens when you run the Ritchie flow on the 4-dimensional examples? Do you imagine that the degeneracy immediately pops up?
Yeah.
Or what?
Yeah. Just essentially, you're just saying that the Ritchie flow can't see the degeneracy. You can't see the measure 0 degeneracy. In some sense, yeah. Yeah, because the singularity is like appearing like densely appear on our end, on R4. Yeah, but the Ritchie flow only detects most of the regular part, which is still like a Euclidean space. Okay. And then once you regularize it, all the singularity just disappear. Just like the DP distance, if you measure the metric in terms of DP or LP, let's say LP, if you measure the distance, like if you measure the metric in terms of LP, then you can't see those singular parts. Okay. And then the Ritchie flow emphasizes it. Okay. So once you move the Ritchie flow, is emphasized so that those parts disappear. I mean, the singular part disappear. Yeah, just like the DP. The DP is essentially like the Ritchie flow. Yeah, or LP.
Yeah, could you